This video is developed to demonstrate how to use iFIX 6.0 to communicate with an Emerson RX3i PACSystems Controller. In particular, in our hardware configuration, we have a 7-slot rack with a power supply occupying the first 2 slots, then our CPU, which is an IC695 CPE 305, followed by a spare slot, and then an ETM, which is a network module card, so the IC695 ETM001, followed by 2 spares. And we're going to be using that network module to handle all communications between that controller and our industrial gateway server, which will be installed on our host machine, and then iFIX 6.0 will be using that industrial gateway server to communicate with the various variables inside our PLC. There's a couple underlying configurations we're going to have to perform. The first is in iFIX 6.0, we just have to make sure we've set it up to use the industrial gateway server as the server software to drive the communications between its database and the PLC. Then we're going to have to edit the industrial gateway server to communicate with the PLC, and then finally ensure the variables that we create in the PLC can be accessed by the industrial gateway server. So without further ado, let's get started. The first thing I'm going to do is just navigate to iFIX's configuration utility, and you can see already we've defined the industrial gateway server within our SCADA configuration section. But just to show that, if I were to click it, you can see the default simulation driver followed by the IGS or industrial gateway server driver. Now, although it is created here, you would normally, under a first-time installation, see this as completely gone. And what you would simply do is under IO driver name, just hit the 3 dots and select your driver. You just click OK and then click Add. In this case, we have it already, so we don't have to do this process, and we're going to just click Cancel. Now, our node name for this SCADA server has been called SCADA. It's completely arbitrary. Just for demonstration purposes, I just call it SCADA, which will be used later on when we define our animations within iFIX's workspace environment. I also have a process database set up as SCADA-DB. Again, completely arbitrary. I've just chosen it as SCADA-DB. And we're done. We're done with the system configuration utility. And since I've already made these changes, iFIX is running already, but normally you'd have to create those changes and then start up iFIX. The next thing we're going to do is we're going to jump to our industrial gateway server runtime environment. And you can kind of see here already I've defined my channel device pair, but just to make sure I show you how this is accomplished, we're going to disconnect from the runtime, and I'm going to simply delete our device channel configuration, and we're going to create it from scratch. So what you're going to do is you're going to click to add a channel. It's going to launch the channel wizard, and from here, depending on what PLC vendor you're using, if it's Allen Bradley or Siemens or Schneider Electric, or in this case, an Emerson PLC, you would choose the respective driver. Now, although we're using an Emerson PLC, it was formerly GE's automation line, so we're going to be using the GE Ethernet driver. So we'll click that, click Next. Let's give this channel a name. I'm going to call it simply Channel, so just simply remove the 1. Use the default network adapter because I only have one network card, but normally you can actually choose which network adapter you'll be using depending on if you have multiple adapters in your computer to communicate with the PLC. So I'll just keep it as default. I just have the 1. We'll use all the defaults for the rest of those settings. Then we're going to click to add a device. And now this is the device level, so more of the PLC configurations. I'm going to just call it simply device. And you'll notice based on the aforementioned channel driver, there's a whole bunch of different family of controllers here that we can choose from. I'm going to choose the PACSystems controller because that's what we're using. And now we're going to enter the IP address for communicating with this controller. Now, this IP address is not going to be the IP address of the daughter board network port on the CPU, so on the CP305. Instead, this is going to be the IP address we've actually statically defined for the network module, so that IC695 ETM001 card occupying slot 4 in our rack. And that is 192.168.1.100. Now, this host machine is on the same subnet, so the IP address of this host machine is actually 192.168.1.200. So it's important to make sure that you can communicate with your, in this case, ETM001 card, because I'm on the same subnet. So just make sure you can communicate. Click next, click next, click next, click next, click next, to the defaults. Okay. Now, in our Prophecy Machine Edition project environment, we assign a controller target name, and in this case, I've called it Demo PLC. Now, this is not necessary by default, but it's good practice to make sure under program name you match it. If you don't match it, you're not going to be able to access program block registers or subprogram block registers. So it's just good practice to make sure you've matched it. We'll just call it Demo PLC, and based on our aforementioned hardware configuration, we know the CPU, so that's CP305, is in slot 2, which is required for this device wizard. So we'll click next and finish. Let's save our configuration and click on a runtime connect. Say yes. Good, runtime replaced. We are done with IGS. Okay, before we jump to the database in iFIX, let's jump to our Prophecy Machine Edition. In this case, version 9.5. I have this demo project running, and if we explore the project itself, we can see we've called it demo with a demo target. There's that demo PLC previously mentioned for the controller target name. In our controller, we have a simple hardware configuration modeling that 7-slot rack. So there's our power supply occupying the first 2 slots, followed by the CP305, and then the IC695 ETM001 network module in slot 4. Now, if I access the network module's properties, there it is. You can see the IP address of the module, which we've defined in IGS under the device properties of our channel device pair. So all communications through IGS are handled through the network module. Now, moving forward under our logic section, I have a very simple main routine or main block. It's the only block in this program, in this project, and it's quite simply just the execution of a couple of variables modeling different data types to help illustrate the various data types that we can communicate with using iFIX's database. Now, for any variable that has a description from iFIX, these are variables that we're going to be both reading from and writing to within our database. Any variables that have the underscore output suffix are just variables that we're going to be reading only. Now, it's important to understand a distinction between these variables in terms of their publishing properties. So anytime you have a variable you want to read from and write to, it's basically essential to ensure you set the publish property to external read write. For variables where you just want to say read only the values, it has to be external read only. Now, if you don't have these set to say external read only, or maybe you had this one to something different, maybe it's set to false or internal, iFIX will not be able to read those values nor write to them. So just be careful anytime you create a variable, set its publish property to external read write or read only, depending on how you plan on using those variables. As mentioned, we've created a whole bunch simulating all sorts of different data types. We've got integers, reals, words, dwords, uints. In this case, it's a real, but we're explicitly defining the reference address for it based on the %r table. Similarly, we have contacts, so we're explicitly defining this Boolean variable based on the %m table. And then finally, we have a user-defined type called UDT_input, whose type is my UDT, and it has 3 member variables, so member 1, 2, and 3, which are a Boolean, integer, and real type respectively. And this is just to help illustrate how do we communicate with a PLC's variable, which might be a user-defined type member variable. So that's basically it. It's very simple, a couple rungs and ladder logic diagram. So let's just close Prophecy Machine Edition and let's jump to iFIX. So I actually went on ahead and I've already defined the what we call blocks in our database based on all the different variables that we've defined in that main routine, as previously shown in Prophecy Machine Edition. Now, anytime you create a database block, you give it a tag name, and then of course you define the block type for that block. And there's all sorts of blocks. In this case, we're going to deal with 4 specific blocks. Just to show that, if I click add, although again there's a whole bunch of them, we're going to choose AI for analog input. This is typically reserved for a read-only analog variable in your PLC. If you want to read from and write to it, we also have the analog register variable. And then finally, the last two are digital input, so just read-only digital input values, so Boolean values, and then digital register for reading from and writing to Boolean variables in our PLC. So for the most part, they're all registers, so digital and analog. We got a couple analog inputs in here as well. So although I went ahead and already created these, there's a common nomenclature whenever we set these up from an I/O address perspective. I'm going to click just one of these, say Boolean input. This is a digital register, and there's a couple points I want to make. The first is the nomenclature. So if I were to clear this, say just go to Sim and go back to Industrial Gateway Server, you'll notice there's a bit of a hint here as to what the scheme is supposed to be, so the syntax. It's quite simply the channel device configuration. We've made an IGS followed by the tag name. So in this case, it'd be channel, as that's the name of the channel in IGS. In fact, if I flip to it, you can see it here, channel.device, very simply. We'll just say no to that. So channel.device dot, then exclamation point, and then the name of our variable in our PLC, which is bool_input, followed by the @ symbol, and then the explicit data type of this variable that we're reading from the PLC. So this is going to be a Boolean, comma, and then 1000 for how often the database will retrieve the value from the PLC. So I'm going to say save, and then we're going to just right click to refresh, and there it is. We currently see it as open. Open just means it's the false value. This is the current value. We can change that too. If we want to, open means false, close means true. I could even say, make this say false and true. And it's just a numeric value to a textual value. That's all it is. So as mentioned, I've got a whole bunch here. The important distinction between symbolic variables and variables in our PLC that have a reference address tied to it are where anytime we have a symbolic variable, it's always exclamation point followed by the variable name, whereas say for a symbolic variable, take this register input, it's just %R because it's the %R table followed by the address of that table. Even here for this motor contact or maybe another register. So that's the distinct definition. If we're referencing user-defined type variables, it's very similar to a symbolic variable as it is a symbolic variable, but we just have to separate the user-defined type to the member variable by putting a little period in between the user-defined type and the member variable we're accessing. So in this case, this is the third member of that user-defined type, which is a real variable, and you can notice here in between the UDT name and the member variable, we have a little period. That's it. Another important thing to mention is anytime we have a register where we're writing a value, it's important under the Advanced tab you have Enable Output selected. If it's not selected, although you've created a register, yes, you'll be able to retrieve a value for that variable, but you're not going to be able to write to it. And just to show what that would be is, suppose I were to bring up Prophecy Machine Edition, and we're going to bring this up and say I just move this over to the left here, and I bring up the database. And suppose I have this bool input. Let's write a 1 to it. There we go. We can see it's written to that variable in the PLC. If I write a 0, okay, it's now off. Now, if I were to select this this block and just unchecked Enable Output and save it, although we can retrieve the latest value, so let's say I toggle this and refresh the database, yep, it's now true. If I put a 0 now to bring it back to false, you're going to get a warning saying, nope, outputs are not enabled. So just make sure if you create those types of blocks, make sure Enable Output is enabled. Let's actually put some context to this. So what we're going to do is we're going to actually, under a workspace, an iFIX, we're going to create some fun animations and data links to illustrate how these values are changing. So under workspace, I've got a very simple and blank picture file. And the first thing we're going to do is we're going to deal with Boolean variables. So I'm going to create 2 push buttons. We're going to call this set to true. And that's a little bit big. And let's create another one and call it set to false. Then I'm going to create a data link on the right. And to give you some context on what we're doing here, the first 2 buttons, are going to be writing 1 and 0 to our Boolean input variable in our PLC, and this data link is going to retrieve the Boolean underscore output variable from our PLC, whose value is determined based on that Boolean input variable. So I want to see the transition. I want to see if I click, say, set to true, I want to see that Boolean output variable change state and give me the value back to me. So let's just make sure we've defined that. If I go to our database, there it is, Boolean output, which is a digital input block as opposed to a digital register, because hey, we're just reading the value, we don't need to write to it. And we can see it's quite simply just channel.device.bool underscore output at boolean comma 1000. And you'll notice under the advanced tab, we did not need to define enable output. This is just a very simple digital input block. So let's go back to our workspace under source. Let's go to SCADA. Let's go to Boolean output and click FCV. And let's condition this a bit. So let's set the color to say black. And let's make our whole digits are set to 1 because hey, this is a Boolean variable. It's 1 or 0. We don't need decimals and we only need one whole digit. Finally, let's do some of the underlying scripts for these buttons. So if I go to edit script, you'll see our clicking subroutine here. Now, the function we use to write a 1 to a Boolean tag in our database is close digital point, followed by quotation mark, then fix32 dot, and if you recall, we called this SCADA server the node name SCADA, so SCADA dot, then followed by the tag name of the block in our database. I believe it's bool input, followed by the parameter of the block that we want to change. So it's .f underscore cv for current value, and that's it. So we can actually copy that, and it's a little opposite when we want to set to false. Instead of closed, we want to open it. And oh, let's just get rid of this s there. It's actually bool input, not bool inputs. Okay, now if we go ahead and just put this into runtime mode, if I were to click set to true, we should see in our PME, we can see, okay, great, we wrote a 1 to it, and we can see the feedback from the Boolean output variable whose value is derived based on that input Boolean variable state. Now if I click set to false, we can see that go to 0. And just to play with those scan times a bit, if I went to that Boolean that Boolean output variable, and let's just say I set that to 5,000, and I said yes, and I clicked refresh. When I click set to true, we gotta wait that 5-second scan time before we can see that change. So in about 5 seconds, we got it. If I click set to false, wait that 5 seconds, and we got it. And that's basically, again, how often the new value from the variable is pulled from the database. So if I click set to true, you can see immediately it is true, and you can see it's out, but we don't have it just yet. Oh, now we got it. So that's basically your scan times. How about analog values? So we have a couple to choose from. Let's create a data link for, let's say, how about this real input variable? So what we're going to do is we're going to go to insert, objects, data link. Let's create a data link right here. And let's set this to our real input. And let's set, keep the defaults, 5 and 2 is fine. Let's set this to black. And what we're going to do is monitor on the output side this real output, which we know is a read only. Now let's just check our database. Do we have that defined? Yes, we do. So here it is, real output. So we're going to just give it a different color. Let's make this red instead. And we're going to change this to output. Looks good to me. And just make sure under the input you have data entry set to in place. If it's set to none, you're not going to be able to write to that variable. Okay, so let's give this a new value. Let's call this 56.44. And we should see a change. And on the output side, yep, we got it. How about 70,000? Yep, we should be getting it shortly. Perfect. Okay, so that's basically analog values. Just for complete kind of sense of iFIX's capabilities, there's also ability to what's called scaling your values, scaling information or scaling values from your PLC into something meaningful. So let me give you a quick example. Suppose you had a analog transmitter, and that analog transmitter spit out a 4 to 20 milliamp value, and PLC captures that as a integer, say from 0 to 32,767, and that is, say, based on a level. So the calibration of the transmitter has been set such that the transmitter reads and sends out a value as a current signal, which means 0 to 100% full. It's a level transmitter for, say, a tank. Well, yes, you could create code in your PLC to scale that raw value to, say, the meaningful 0 to 100% fullness, but you could also do that in iFIX using signal conditioning. So in this case, we're going to explore this 15BN signal conditioning type. Again, takes a raw value from 0 to 32,767 as an integer and scales it based on the low engineering unit value and high engineering unit value of our block. So if we jump back into our database, let's just create a brand new variable, an analog input variable. Let's call this level output, and let's use the industrial gateway server driver channel.device exclamation point, and I think it was it was int underscore input, because we want to use that integer to drive our level here. So let's just say it is 0 to 100%. That's our low and high engineering units, and again, this is a percentage. And we're going to set the signal type to 15BN. Let's save that, and there it is. And we're going to save the database, and let's go ahead and change some of this. So I'm going to set this to our integer variable. There's our integer input, current value. That's fine. Let's get rid of 0. There's no decimals in integers, so just make sure it's 5 whole digits. And this red will be our conditioned level. So if we go to SCADA, where's our level output? There it is, FCV, and we know this is 100% is the max value, so we'll put 3 whole digits and up to 2, because we want the 2 decimal places. So let's go online. So what is 32,767? That should be 100%. That's our max. Cool. How about 0? 0 should be 0. Okay. How about, say, 16,000? That's roughly 50%. Okay, 48.83. Fair enough. How about 18,000? Cool, 54.93%. So as you can see, iFIX can be used to condition raw signal values, something more meaningful, or you can have that accomplished in the code of the PLC itself. The flexibility is there, though. And that's about it. So I hope this video was meaningful. Again, what I wanted to prove out here was how to create different types of database blocks, and then having those blocks communicate to a PLC to read values and write values using a variety of different data types. And then, of course, how to set up this whole communications path using the industrial gateway server driver. So thanks for watching, and thanks for listening.